at how do we solve the problem that we looked at in the last video. How can we prove to a third party that this is indeed the response that came from a certain website? Cool. There are three approaches that we're going to be looking at. The first approach we're going to be looking at is the TEE approach. It's probably also the simplest of the constructs. Okay, so you have the server and the client. They're doing this TLS handshake, and once the handshake is done, they are encrypting and decrypting the data. Cool. This is the regular TLS handshake, but what the TEE approach says is, hey, instead of running the browser on your desktop, run it inside a magical computer. This magical computer is called the TEE. There are a few TEE providers called SGX by Intel and Nitro by AWS. Both of them have different properties, but these are the two major offerings right now. So what a TEE does is you get the guarantee from Intel for two things. If you're running on Intel SGX, you get two guarantees. Number one is privacy. That is, any computation that is being done inside the TEE, including the data that is being generated, is all kept 100% private. Even the physical owner of this TEE does not have access to the data that is being generated. What that means is there's a shared secret that is generated by the client and the server during the TLS handshake, and nobody other than the server and the TEE have access to this, and even you who own this TEE do not have access to the shared secret. What that means is you can then do the encrypted request, you can do the encrypted response, and output from the TEE what the response was. And that is where the second property of the SGX comes in, which is integrity. You get another guarantee from Intel that the computation that ran inside this black box was exactly what program it was fed with. You know for certain what program was being run from here to here. You know that's the regular TLS handshake. You know that a particular request that was probably sent to the TEE was encrypted and sent. Encrypted response came back from the server, was decrypted over here, and the decrypted response is what is being spit out. So you're basically saying that, hey, I trust this response. I trust that this user has a bank balance of 1234 because that is what the Intel SGX is. Because I trust Intel, that Intel is not trying to collude with my friend and trying to cheat to me, I will trust this response. Right? And that's the simplest of the constructs. Basically, you trust Intel, and if you trust that the Intel TEE has not been compromised, nobody's been able to figure out the shared secret using a microscope. If all of that is true, you can trust that the response that is being spit out by the TEE is actually the response that came back from the server. This is a pretty neat construct. The only thing that is probably a drawback on this is the fact that you have to trust either Intel or AWS on actually running this privately. And there have been, unfortunately, multiple instances at which this assumption has been broken and TEEs have consistently been hacked and these properties have been hid in the past. So you need to be aware that there are certain constraints to using TEEs. There are certain trust assumptions that you need to be aware of if you're using this process. It's not a shit on TEE approach. It's just that all the approaches that we're going to be talking about today will have certain trade-offs. And this is the trade-off that you're making if you're using the TEE approach. Okay, so this brings us to the second model, which is the MPC model. So again, you have the client and the server. But what we do in the MPC model is we introduce one more entity. And we introduce that entity behind the client. We'll call this, let's say, a notary, the client. Okay, so what happens over here is the client sends the client hello, the server sends server hello, and then sends the server, and then it sends its public key, the generator, and a signature. Now, this is the regular setup for the TLS handshake. But here's where things change. So in the previous TLS handshake concept that we saw is the client would pick a secret, a private key. It would use the generator to generate a public key and send that across, right? But that's what we're going to change over here. What we're going to do over here is an MPC. An MPC stands for multi-party computation. It's going to say, hey, I need to create a private key. And the notary and the client will engage in an MPC in which certain data is passed around. And together, they come up with a private key A-. Now, the important thing is neither the notary nor the nor the client has access to A dash. You can think of it as they have a half and a half. Right? So both of them, you can think of them having two shares of the secret, right? So half of the secret is with the notary, half of the secret is with the client, but both of them do not know what the full key is. Okay, now we need to generate a public key that we can send back to the server. So we know the generator. What this will do is do another MPC, that's like some data that is being exchanged, some computation that's being done that might be outside the scope of this conversation. But at the end of this computation, the output is g to the power a dash, right? So in this computation, the client is providing its share, the notary is providing its share without ever exchanging their respective shares with each other. But the output of this MPC is this public key, which is g to the power a dash. And this is the secret key that we had selected. This is going to be the public key, and we're going to send this public key over to the server. The server would accept this public key and generates its shared secret, and then the MPC again kicks in, which you generate g a dash b. So this is the shared secret. Neither the notary nor the client has access to g a dash b. It's only through the multi-party computation that they can do computes using their respective halves, but they never have access to the shared secret itself. Finally, when they're sending an encrypted request, they again need to do this multi-party computation and encrypt it using this shared key that is not known to either of them, but is known through the multi-party computation. They do the encrypted request, the server sends the encrypted response as is, and then you decrypt the data again using an MPC, because you need GA-B over here. And the response can be signed by the notary, and you can share this response with a third party along with the signature. The notary would sign this response only if this response is an output of the decryption using the MPC that they did at the last step to decrypt the data. If the notary is honest enough in saying that, hey, I will sign data only that is an output of the last decryption in the MPC, as long as that is true, the third party can be sure that this data actually came from the server. This is actually a pretty secure construct. Like in the previous construct with the TEE, we saw that sometimes you could have a breach of the SGX itself using lasers and microscopes and whatnot, but this is like more cryptographically secure, right? The only bottleneck in this construct, at least at the time of the recording, is there are like a lot of MPC that's actually happening, which means that it just takes time, right? It's probably the slowest of the three constructs that we're going to be looking at, which does not have implication on security per se, but has downstream effects on user experience. So that is something that you might want to keep in mind when you're using this particular construct. That concludes our second approach. That brings us to the last construct. Again, you have the client, you have the server, and instead of putting a notary over here, what we do is we introduce what's called a proxy on this side of the client. So now the client is going to do the TLS handshake, and once the handshake is done, it would send the encrypted request, get back an encrypted response. And all of this data is being passed through the proxy. And the proxy, even though it's looking at all of the requests that are being sent as part of the TLS handshake, cannot determine the shared secret for this TLS session, because we've seen that the Diffie-Hellman key exchange works even if there is an external observer looking at all the messages as part of the key exchange. So the shared key is not known. So let's say the key is available to the client, the key is available to the server, but the key is not available to the proxy. Right. What that in turn means is it is only looking at the encrypted request, it's looking at the encrypted response, but it cannot decrypt it. And then it's going to give an attestation that, yes, I saw encrypted response go from server to client. Right? So it gives a direction. And then the client can take this and go to a third party and say, hey, this is the encrypted response that came from the server. And you can see that the proxy has attested to this information, that this is the encrypted response that actually came from the server. And here's the key, right? So using this key for the encrypted response, you can figure out that my balance is 1, 2, 3, 4, given that you trust the proxy for the direction in which the data came from, right? So this data that you're feeding into the decryption algorithm is also signed by the proxy, saying that this is indeed that came from the server to the client and not from the client to the server. So this is indeed the response that was coming back. And if you know the direction of the movement of this encrypted data, you also know that it is a response, and you know that it is coming from the bank, and thereby you can be sure that this is the data that has been sent by the bank. Right? As you can see, there's a much simpler construct. There are not too many extra steps that have been added. So this is like very efficient, right? So TEs and the proxy mode compare well when it comes to performance, but the MPC model is more secure than the proxy model because there's one attack that is possible in which a hacker is able to come in between the proxy and the server, introduce one more entity, and feed incorrect data over here. The proxy will see that, okay, this is the response that is coming in this direction, but does not know the source of this vector. It just knows that it's coming in this direction, but does not know that it's coming from the server. So it has to trust that there is no man-in-the-middle attack between the proxy and the server. So that is the trust assumption. This is a fairly sophisticated attack to pull off. It's non-trivial. Basically, you need to be in the same physical network almost as the proxy to be able to actually pull off this attack. So for a lot of use cases, this may not be a big problem, but there are certain use cases that I can imagine in which you need 100% security, that there is no man-in-the-middle attack. In those use cases, you need to be again aware of the trade-offs that you're making. Cool. So those are the three types of solving the problem of provability of data from a server. That is TEs, MPCs, and proxy. Again, if you notice, none of these three models that we talked about did we talk about zk at all, right? And that's what we're going to be talking about in the next video. So far we've been able to establish that we can add provability to TLS, but we've still not looked at how zk can supercharge this. We'll talk about that in the next video.